thank you. I know this is the last one of the day, which is always hard. So I appreciate you coming in to check this out. Today I'm going to talk a little bit about Columnar HBase for translytical workloads. And what I mean by this is really making HBase performant for both real-time processing and analytical processing, and kind of pushing the envelope in performance on both ends. So hopefully by the end of this, you'll see that I've tried to push the envelope on how fast HBase can return a single record and how fast it can perform analytical operations. So the first thing for me is, conceptually, how did I get here to want to build a translytical columnar sort of setup? So our technology path is Splice Machine. We kind of, like everybody, you start with small releases and you work your way up. So our 1.0 release had a single model for transactions, execution, and storage. All the talks I've heard about coprocessors and those blowing up and how to, put them somewhere, make sure you don't use too much memory, all that fun stuff. We hit that. So we used internal coprocessors. All of your aggregations and joins and things happened inside coprocessors. And we put everything in a hashed transactional table. So that was nice. It gave us a good prototype. Hey, I think this is going to work. 2.0, we went to a hybrid execution architecture. We didn't do that for kicks. We did that because 1.0 had a lot of problems having a single execution architecture. What does that mean? Basically, any query in Splice Machine can be run either in real time, just in memory, or it can be run as a set of Spark instructions. So for analytical execution, you can do in memory, or you can run it against actually in Spark. And one of the powerful things that we did there is we read HBase store files directly. So instead of going through the front door of HBase, we went directly to the file system, and then we did an incremental delta with what's in the mem store and put those together, and you still get a consistent view of the data, but you're not pulling a ton of data through HBase. You're using the file system, which generally scales a little better. We also moved, I think Monty talked about this earlier, we moved compaction to Spark. Once again, that wasn't because we wanted to, it was just compactions basically made a lot of our performance results unstable. So if a compaction kicked off, HBase would behave differently. So we wanted to remove that and have it scheduled in Spark. So with 2.0, we get resource management, we get scheduling, we get containerization, we're on Yarn, a lot of good things in the execution space. 2.5, we moved to a hybrid transaction model. Our first transaction model it's hierarchical, but we just wrote it to a table. The reality is, if you're trying to do an in-memory, like a single row insert or something smaller, you don't need the heavyweight piece of our transaction model. So we kind of slimmed that down. And we also had read-write columnar capabilities, so Parquet, Orc, stuff like that. Pretty straightforward. 2.6 came in. We launched the database as a service. So we basically took Splice Machine. We used DCOS and Mesos to schedule the bringing up of a Hadoop cluster, HBase, and Splice Machine, all with the set of instructions. We built in alerting features where if a service isn't responsive in so many seconds, kill it, restart. And that's what runs our database as a service up on Amazon and now Azure. And what I'm kind of here to talk about today is 3.0, which is a path we've taken. I call it a PAX storage model, and I'll get into that in a little bit deeper. But, how many people here are happy with HBase analytical performance? And since everybody uses HBase here, that's not a good sign. So I wasn't either. So I'm with the team here. So I was really disappointed because I thought we were really close with the Spark execution engine. You could see we were almost there, but not quite. So what I'm going to talk about today is a single storage model for analytics in real time, and then talk about how that then goes into pipeline and code generation in Spark, and how this actually allows you to perform quick analytical queries. So what are the problems I'm trying to solve? I usually try to say, what's the problem statement? Analytical execution speeds are slower than the columnar counterparts. So if you're running Parquet on Spark, it's faster than running against store files in HBase. And we've kind of accepted that as a community. Write amplification. So when you're jamming a bunch of data into HBase, we've kind of accepted that there's going to be a lot of write amplification, i.e. data that's rewritten, and it creates significant network and disk activity because the size on disk is pretty large of HBase as a community. For Splice Machine, we had really advanced statistics that we did with Yahoo, with their data sketching algorithms, but we didn't use it on the execution side. We used it on the planning side. So that was another thing that was problematic for me. Just looking at either customers or people who have used our database, low cardinality columns take up a large amount of space. So people who have, a column for California, and you're like, couldn't you put CA? Couldn't you make it, char 2, those sorts of things. Another challenge we had, if you update a single column in a row 20,000 times, we had 20,000 entries in the storage structure because we have an MVCC model, which we inherited from HBase. The custom encoding and decoding that we used, I thought was pretty confusing and not optimized. Intermediate results in Spark. So once you kind of are outside of an optimized storage structure, an optimized columnar structure, your sorting and hashing implementations are going to be real object heavy. So they're going to have, they're going to consistently try to do a comparator and run through all this where you're not using, and I'll show what we did with Tungsten here in a second, but basically what happens is you're not getting really efficient sorting implementation. Backups are expensive, so you have this bloated data structure. Now you're trying to back it up. When you start moving terabytes, petabytes of data, that becomes problematic as well. And then one of my big challenges, do we live in a world where schema optimization occurs? And what I mean by that is, users will put California versus CA on a table and have it denormalized, and that table has 1.5 trillion records, not knowing that, well, California is going to be a lot more bytes than just CA. And people are dismissive of that. And it's kind of falling on us as engineers to try to come up with a solution. So when I looked at this, it really comes back to HBase. And it's really what's under the hood. It's not the coprocessor on top or anything like this. What is under the hood? And in HBase, as we know, we have a key value store. We have an index. And then inside those indexes, you have data blocks. So usually, in our case, Splice Machine, 65,000 records in a lot of our tables. So you have these data blocks. And I'm going to have Stack demonstrate here to make sure everybody gets it. Can you search for the woman back there? Using the HBase. Now this is a sorted data block, and let's look at Stack Go. All right. So that's actually how HBase works. It's a linear search inside of a data block. So we have a login sort of structure to get to the data block, but once we're in that data block, we pull a stack and we kind of meander around. Okay? So what's the great thing about this? It's an append-only structure. Like I said, there's an index on top of this, so you get a nice login with the index. But within the data block, it's really CPU intensive, and it also has really bad cache characteristics of the CPU. Because think of what he just did. He meandered around all the data points that he saw, but discarded. It's really, really expensive. The storage is actually pretty large as well. So in the case like Splice Machine, we may have a secondary index that has 4 keys. Well, the first 3 are probably the same. So it'd be nice if we could use some sort of tree structure so we didn't duplicate all of that data. The data here is stored row major. So that means your regions are split up by row keys, and also row minor. So inside, you just have your key values stored in a big block of bytes. And then the compression and coding is applied at the block level. And the block cache representation is uncompressed. So that's just a statement of fact. Does that seem reasonable to everybody? So this is what's under the hood. Okay. So This is a paper from 2002. And in the paper, the key part of it is he's looking at how you're storing data pages. So in our case, data blocks. And his hypothesis of the paper is basically, look, it's great to have, for transactional performance, to have a row major at the biggest partitioning piece of it. But inside of a data block, it'd be nice if it was stored in column major or in a columnar structure. Now, the point, we all know that is, everybody's seen ORC and Parquet, so we all believe that columnar makes analytics faster, and we get the sense of why the vectorization works. But what's revolutionary about his approach is it actually made transactional processing faster. And that was the part that kind of wakes you up. So what this paper claims is that by storing the data in a columnar structure inside the data block, your transactional processing, our single gets, are going to be faster. Okay, so are we revolutionary? No, that was 2002, right? This is from some stuff I grabbed from some of my Google friends, and they came out with this strategy after we started working on a splice machine. They called it RESI, which is basically if you read what they're saying, blah, 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 essentially the PAX layout. So what they're realizing is even if you're running Spanner or you're running something on top of Bigtable, you're realizing that you have a schema. It could be a flexible schema, yes. It can be a hierarchical schema. It can have structs and arrays. But you have some sort of schema concept. And if you can store it in that schema concept, you can then store it in a columnar structure. Luckily for us in the Hadoop community, we have columnar structures. Okay? So if you look at HBase storage reimagine, so big doesn't have to equal slow. It's an append-only structure because we're keeping it within the HBase structure of how it works. So same H file. The index to data block seek is similar as before. But within a data block stack you want to demonstrate, we have an index. And what does that index do? It says go to 1, 2, 3, 4. Sorry about that. Row 4, position 1, and he doesn't have to meander through all your data. Better yet, that index can come first, and the data can come last. So as far as the CPU perspective, he's just messing around with the index when he's seeking. Okay? And the big thing is if you describe it to somebody, it's row major, because we still have regions and blocks, and they're stored in a sorted order, right, by row key. So that doesn't change. Just within the data block, what we're wanting to do is have it what we call column major, or column minor, I should say, storage. So within the blocks, they're going to be columnar. And they're not just going to be columnar. If you just jammed like Parquet or ORC bytes in there, we still have stacks, little, I don't know what we call it, strutting around, right? So that's not good. We've got to be able to quickly look at data in a constant time characteristic. So what that requires is a tree. I believe someone had told me, was it Alibaba or somebody else had hit this problem as well. I don't remember who. I'll have to check that. But you need a tree. Why do you need a tree? Because you want to quickly be able to seek in constant time to your row and then get it from the columnar structure. Okay? Just like stack could go immediately there. What's even more important is compression and encoding. So I've got my row key in a really nice index structure. It has common keys, and I'll kind of show you our index structure in a second. But what's really cool is you have run length and dictionary encoding. So that California problem goes away. That's now a dictionary entry that you're pointing to. It's applied at the column because there's different encoding for different data types. And we already know the types of those columns. And the block cache representation is actually compressed. And when we run this, and what gives me kind of makes me take a step back, the data is actually 4x smaller on TPCC and TPCH data sets. Now, whatever data you have, divided by 4. All your compactions, divide them by 4. All your backups, divide them by 4. All your replicated environments globally, divide the space they need by 4. So this is significant for us because as you have a bloated storage structure, it's just hard. Everything's harder. Compactions are harder. Scanning for analytics is more difficult. Backups are more difficult. So what are we talking about? Just break it down. It's an HBase structure, 2 column families. We have 1 column family for active data, another column family for redo. It's like a classic Oracle model. The 1 version in active, and then n increment of versions in our redo structure. And then you have your active data block. What does your active data block have? Simply some bytes that represent your tree, and some bytes that represent your columnar, in our case, orc bytes, an orc stripe. Okay? So if we want to load a block, we just say, point to those bytes, and we're loaded. Once we get inside a block in HBase. There's no building a tree, there's no building a columnar structure, we're just pointing to the bytes. Okay? And the columnar structure, like I said, is that orc stripe. Okay, so let's talk a little bit about the tree. This paper was written by Thomas Neumann, I believe. Newman is his name. This group actually, I believe now their technology is inside Tableau. I think they were acquired by Tableau, if I remember correctly. And this isn't for a massive scale-out database, but for in-memory quick processing for Tableau. What's cool about this is this kind of lays out for us how to build a very fast in-memory tree. And the characteristics are the most important thing. You have constant time operations. You have prefix compression. So in the case of Splice Machine, we like, I think we were talking about 7 indexes and different tables we want to create indexes on. It's absolutely critical that we have prefix compression. So those repetitive keys don't take up a lot of space. Ordered iteration, both forward and backward, because we have reverse scans, unfortunately. So we had to implement that both forward and backward. And you have prefix-based iterations. So if you can think from an HBase perspective, you put in 4 keys or something inside your scan. This is where you want to begin your scan. There's 4 node types that are kind of informational nodes, and then there's a leaf offset is your other node type. So let me go into the nodes a little bit. And here I'm basically trying to show you actually what spits out from HBase when I actually flush data into HBase. This is what it generates. It generates a tree and basically a compressed representation of that tree. So every node of the 4, 16, 48, and 256 has a type that tells you, hey, I'm 4, 16. Has a number of children, so somewhere between 0 and 256. Now, obviously, node type 4 can only have 4 max, 16 max, 48 max, and 256 is obviously the max you can have for a byte. And then as you put in more data than 4, it'll transition from a 4 to a 16. So it's a dynamically allocating tree. So you have your number of children, your partial length, which if you look up here at the right under root, this is a 16 node here, and that 555B 55, that's the partial length. So those are repetitive bytes in the keys that are underneath it. Okay, so that's your. And then node 4, you have 4 bytes for your keys. So that'll be the next byte that comes along. So if you start with CAL for like California, I will be actually inserted into one of the keys. And then you can, that's kind of how it goes to the next level. So that it has a set of keys. Now this is really cache efficient because you can just look and say, hey, I can look basically on those 4 bytes and say, do I have a child that represents that? The children are 4 times integer. So when I first did it, I did it based on longs. So I did it really kind of classic implementation. And what we found was the long actually created really an actual large structure in memory, in the byte arrays. Because you don't need a long to represent what's in a data block. You just need an int on top of your address position. So node 4 has everything in the abstract node, just its information as types. Node 16 is very similar. You have 16 bytes for your keys. That's the next byte that's there. And then you have your children, which are your pointers to the node underneath it. Node 48 is a little bit more interesting. It has keys of 256 bytes. So basically, it's going to have any of your pointers to any of the next bytes in the tree. And then it only allows 48 children underneath it. And 256 doesn't have any key pointers. It just uses basically, it's smart enough to know that if your byte position's 51, you just go to the reference in 51. So those integers are your address of your tree plus where the location is located. So you can immediately jump from, I need to go down the tree, and you're jumping in the byte array, the byte buffer. The leaf is similar. So the leaf offset, it's a type. It has the key length, so how big is your key, your offset, and then basically your key. So whatever's left of your key, the variable length will be placed there. If you look at the structure, what's really powerful about it, really CPU cache friendly. If you think about it in a nice way, you're just comparing the number of bytes that you need to get to where you're going. So you're not overly, what's the best way of saying it? You're not over and over again trying to compare all the keys. You're just comparing the small bytes based on that offset. So much faster than kind of a current sort of structure. So what does this look like? And I kind of put some code up here, so bear with me, but I want to give you kind of a flavor. So it's just a byte buffer backed implementation. What does that mean? So it's not like a concurrent skip list where you have a bunch of objects in the JVM and all kinds of fun stuff going on. There's none of that. Okay, so it's just a byte buffer. You allocate basically a page or a block, and then inside that you're actually just doing puts of integers and mem copies and array copies. So all low level, no objects. So the structure I laid out is just a big set of bytes with pointers around it. And then on the read-only, one thing that's interesting is, so as we're flushing data, we'll write into this structure. But what's kind of cool is when you actually flush it, there's a bunch of different compression optimizations. So for example, on like the node 4, you don't need 4 ints if there's only a length of 2. So you can knock off those 8 bytes. So this is all about just how many bytes you need to represent this tree. Now, just real quick, why is this important? Because now all of a sudden, inside your data block, you have a tree. To construct your tree, you just need to point to the byte buffer. So you don't have to reconstruct it or anything. You have the bytes, it represents the tree and the address, and you're right there. Okay, one other thing that I've added, and I was just going to go on these. This is a little bit off topic, but I thought it might be interesting for the group. So what I showed you first is kind of a read-only or a single writer sort of concept. This is now single writer when you have multiple readers. So you're going to use a ring buffer similar to our write-ahead log structure for the write. And then for the read, one of the things that's really nice about a single writer, then you can use RCU, so read, copy, update semantics. So I've basically extended, in essence, our tree to be able to support read, copy, update. Why is that nice? You get a lockless implementation, or relatively lockless. And then the thing that was the biggest for me, so I'm writing this little art, putting bytes everywhere. JMH blew me away. The fact I didn't use it more when I was writing some other low-level pieces, shame on me. Because it really quickly allows you to do performance benchmarking of that piece of code. And for us, it was mostly around inlining and byte buffer allocation. And what I mean by inlining is keep your methods small, don't have recursions, things of that nature. This made a huge difference for us. It also caught one of the major problems I had. When I first flushed the tree to the bytes, what I would do is I would flush it all the way down the left side and then traverse through the iteration, when in actuality I needed to flush each level first. That was more CPU friendly when you're wanting to fetch data. Okay, so you came for a columnar talk, and all I've talked about is an index structure, right? The reason why we don't have columnar in HBase is that index structure. Because anybody in this room could grab a Parquet library and slam data in the Parquet library or in the ORC library. The real question is, can you build a structure that's performant and quick? It's really that tree that becomes the linchpin of making HBase perform in a different way than it currently does. So you have the nice thing about this. So we've got our bytes in a length that say, here's the tree. Now we're writing to ORC. That's not rocket science, right? So for us, we have SQL 2003. And so for every one of our data types, we have a Hive ORC type data type. Pretty straightforward. How many people have written like an ORC writer or something? No ORC people. But they're pretty straightforward to write. So what we do is we do add a few things for our transactional piece. So the version, that's your what version of the row. The type, which is your whether you're put or delete. Sequence ID, which is being generated from the right. Tombstone, whether it's deleted or not. The transaction ID is splice machine, which tells you whether that transaction, what's the state of that transaction. And then the effective timestamp. So the effective timestamp, once you've resolved that record, you either say, hey, this thing's good as of this time, or it's -1, it's rolled back, and get rid of it. All right. Okay, so how do you do this? It's written into HBase, right? There's data block encoders. So if you think about it, you don't really have to change HBase. You're not going in with the hand grenade and saying, I've got to change the whole read structure of HBase. I've got to get rid of this. No, it's just a data block encoder. So really simple. Hey, I want to start a block encoding. I want to encode a cell, and I want to end that. This is really simple code, and then you have a seeker. So if you look at what you're wanting to do, you want to say, how do I write and flush data? And then how do I seek and search inside of it? Okay, so how do I write data? Well, that's pretty easy, right? You have a radix tree insert. So you insert your row key in the radix tree. You write those 6 values that I talked about that we need to understand the state of the row and some of the information that HBase needs to understand the row or quote cell. And then you write the rest of the fields that you've supplied into the columnar structure. Does that make sense? It's stupid simple. You have a tree, jam the row key in with where you are in the counter, write it to ORC, which there's like tons of stuff online about how to write it to an ORC. So you have these 2 byte structures, and you copy them on the byte buffer in the block for HBase. Does that make sense to anybody? Okay, so it's a really basic strategy. So nothing fancy at all here. Okay, how do we want to seek? Okay, well, I want to set the current buffer. So this is inside for people not familiar with HBase fundamentals, there's basically this seeker concept. So when you have a block encoder, you can have a seeker. And what does a seeker do? It understands the underlying structure and how to seek to a cell. So if you say, hey, I want that cell, it understands internally how to seek through that. In our case, it's a tree. In the case of HBase, it's the meandering linear search. And then how do you create the tree? You just grab the buffer. Throw the buffer in, you've got the tree. Well, how do I get the columnar part? Once again, just grab the buffer and throw it in. Because both of these are just the bytes that are sitting there. Now let's talk a little bit about the read pipeline. So remember at Splice, we kind of decided that transactional processing and analytical processing required two different strategies. They're just fundamentally different. So in the in-memory execution where you're running a simple select of 5 rows, you have that custom encoded seeker that I showed you. We wrap it in a lazy seeker because all over HBase it'll say seek, 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 but you don't want to be unwinding the columnar structure until you need to present it. And then we just run through the normal LSM flow because you don't need that kind of performance on give me 4 or 5 rows. So it just runs through the normal LSM flow. Now on Spark execution for large, that's a little different. So we already know that we read the file blocks directly. We already have a store file piece of this. Then at that point, what's cool is then you can do a vectorized LSM merge. You can do a vectorized snapshot isolation. So what we used to do row by row to resolve, we can now run it against 1,024 items, and we can run them in a vectorized manner. And when I mean vectorized, you mean a tight for loop, and you're just focused on that little functional piece. It's really friendly to the CPU. And then what's most important is you can operate on the column vector in Spark. So think about this. It's not just enough to store it small. It's not enough to get it out quicker for searching. You got to put it in your execution pipeline so that your execution pipeline can operate on it in an efficient manner. So in Spark, that's this column vector concept. So you basically have 1,024, you push them up, and then it has references to data blocks. So that's on the read of for Spark. And then a nice side thing of this is for shuffle preparation. So shuffle is a fancy way of saying, I've read the data, now I need to move it to another cluster because I want to do a join or some sort of data movement, right? An aggregation where I've got to group it all in one spot. What's cool now is since we're on the Spark path with our data model, because we're using ORC, which is kind of a known structure for Spark, it'll do code gen. So when I want to write the record, instead of me doing some sort of serializer or some object serializer or cryo serializer, I don't have to do that. Spark will actually generate bytecode that's optimized for writing those bytes. It'll do byte buffer-based sorts. So it's actually just going to write it to a block of bytes there in Spark and do pointers similar to what I'm doing for my tree in their sort mechanism. So they're not going to create a bunch of objects there. That's huge for us. That's about a 10 to 100x shuffle improvement. So when we want to sort a bunch of data, this is absolutely critical for us at Splice because you have to do that extremely fast and efficient. So if you sort 200 column table and you want to just do an order by on it, that's a lot of sorting of data to kind of get a sense. And this, like I said, really does the encoding and code generation quickly. I'm just going to go back to the problem statement. So analytical execution speeds are slower than their columnar counterparts. We addressed that, right? And we have a columnar structure there that we can use that ORC file and read it in Spark. Write amplification. So this is a big one because compaction is a problem. And you think you solve it by moving it off to Spark, but you really don't. You're still moving a ton of data around the cluster. But if you take that amount of data you have to rewrite and you divide by 4, you can kind of live with it a little better. I don't know if I touched on this. The ORC bytes actually have statistics in them. So they'll have they'll have your basic range type statistics, and they also have a Bloom filter. So if you're doing like needle in the haystack search, but you don't have an index, it can just discard that entire block of data, which is really powerful. Low cardinality columns take up a large amount of space. We don't have to worry about that because we have dictionary encoding now. If we update a single column or row 20,000 times, we now have a redo structure that we put in place, so you just still have your one active record. Custom encoding, decoding, gone. So everything is standardized, Spark, Tungsten, and then when you're encoding, it's a version of ORC. So you know what your data looks like in the bytes. Intermediate results now basically are no longer, doing a bunch of comparator and creating a bunch of objects and doing a lot of fun things. It's all direct byte manipulation. Backups are expensive. Cut that into, it's about 1/4 of the size now. And no, we don't live in a world where schema optimization occurs. But with dictionary encoding, we'll get that storage, so we can be less of jerks to people who are wanting to create tables or use bloated data structures. All right, with that, I can take questions. I appreciate everyone. This is a pretty dry topic for one of the last ones of the day, but I definitely appreciate your time. If there's any questions, I'll be up here. That's a great question. So that's something we're considering, because I think for me, even just putting the tree into HBase, and let's say you just have the tree in your bytes like they normally are laid out, that's I think what the Alibaba guys were doing, because it cuts down on your CPU usage. It just allows you to get there faster. So I think that's a good idea. But I think this is something that should be in HBase. You should have a way to present. And when I say a schema, I'm not saying like, you know, ints, longs. I mean, you can have structs, you can have arrays, you can have complex pieces, but this would change the way HBase functions. And for HBase to kind of make a step up, it's got to change its physical representation of data. So long story short, I would love for that to happen, and that's something we're considering. It's a great question. Yeah.
Do you have performance comparisons between, regular org and HBase?
Yeah, so it literally is the orc code in Spark. So it's just like orc in Spark. The thing that's a little different is I did write my own vectorized reader for orc, and I used Presto. So it's not, I shouldn't say I wrote it. I took Presto's orc reader, made some modifications with our data types, and then I used Presto's orc reader, which I've found to be the fastest one out there. And it basically performs on par with their orc reading. So what you've done is you've basically gone from HBase being this dog to where you're basically just reading orc files from the file system. So it's just, especially with our ability to read, like I said, directly from the file system. So good question. I'd love to do a lot more on the performance side here. I just haven't, to be honest, haven't gotten there yet. But just on the basic stuffs of like the first queries in TPCH, significant improvement. The one thing about splice, reading off disk isn't the thing that kills us. It's the when you have like a 6-way join and you're writing in Spark, those intermediate results. So yes, the biggest thing for us is that actually that 10 to 100x on the encoding of intermediate results. Yeah, that's the thing that always killed us. And one thing I didn't point out, and I probably should have mentioned, with this structure, we also get decimal optimization. So you don't have to store decimals as big objects. You can store them as longs if they're like 12.2 in most of the benchmarks. So those sorts of things really help performance. The decimal is the big one. So if you look at like TPCH or DS, they're really just seeing if you have an optimized decimal implementation. Yeah.
What's the stripe size you're using? So org usually has big stripe sizes, right?
Yeah, so it's just a single stripe. So basically it's the block size of HBase. Well, I'm starting to bump that up because the reason why, in my opinion, why HBase says use small block sizes is because of the stack effort of what it's actually doing internally. So if you expanded that, you would burn a lot of CPU doing a linear probe to find your byte. Now that you have a tree, I think you could bump that up. So that's one thing I want to try to test. But I've started to bump that number up because if you think about the overhead of the stripe, you have the statistics. There isn't a decent amount of overhead. So if I can bump that up, that would be the most beneficial.
Right, but if you make it bigger, then your random lookups will be slow, right? Because you have to.
It's a constant time lookup. So remember, it doesn't matter how big the data block in HBase is. It's still constant time by that rate X tree. It's a constant time lookup.
But you have to read it from disk, right? The entire block before you can actually.
Yeah, you still have. Yeah, you're right. You still have the data block you're reading from disk. That's correct.
So that will be slower.
Correct. But the one nice thing about this, and one thing you see immediately just from interacting with it, like when I started Splice Machine with this, it's just different. Everything's just snappy. And you're like, well, why is it so fast? And then you realize 4 times the data is in the block cache now. So everything that was kind of stretched as you loaded data, you've just changed that factor. All right, I think that's it. I'll let everybody get out of here. Thanks, I appreciate it.